Welcome all of you to the today's session.
So the last class we discussed about the concepts of sedimentation. So in this class, let us focus more on numericals. So before that, just go through this content. So Unacademy conducting mock exams, enroll as soon as possible. Okay. Sorry.
So let's start today's session.
So we are going to talk about numericals, how to solve numericals related to plane sedimentation, retrospecting whatever we discussed earlier. Retrospecting the concepts of plane sedimentation. Once again. Retrospecting the concepts of plane sedimentation.
So to design
sedimentation system, the first thing what we need to work out is settling velocity of the particles. Settling velocity is very important component that is to be worked out. So which vary from particle to particle. Settling velocity of any particle that you can work out by using Stokes equation 4 by 3 g into rho p minus rho w into d by cd rho w. This equation is called Stokes equation. And this is generalized equation which can be used for particle of any diameter, particle of any size, right? Particle of any size, in any medium, for any flow regime. You can apply this equation. So where Vs is known as settling velocity of the particle. So normally in plane sedimentation we maintain laminar flow condition. For laminar flow condition, right, this equation reduced to simple form. So Vs is equal to G into rho p minus rho w d square by 18 mu, or otherwise G into S minus 1 d square by 18 mu. Either dynamic viscosity or kinematic viscosity are not given for laminar flow condition. Sometimes we use Hazen's equation 418 into S minus 1 d square into 3t plus 70 by 100. So this much idea is there, more than sufficient for laminar flow. For transitional flow conditions, generally we use modified Hazen equation for transitional flow. Same equation 418 S minus 1 d into 3t plus 70 by 100. For turbulent flow condition, So settling velocity is equal to is 1.8 into root of g into s minus 1 into d. So normally in plane sedimentation by default, we maintain laminar flow condition. Therefore, these equations only we use. We don't use other equations. By default, we use these equations. Okay. So all these equations are derived from Stokes equation only. Stokes equation only equation is basis to work out all these things. Okay. This is how we can find out. Then in addition to that, we have discussed about design concepts of sedimentation tanks. One is surface loading rate or surface overflow rate denoted by V0, which is equal to Q by surface area of sedimentation tank. Or sometimes, so using the surface loading rate or surface overflow rate, we can find out surface area of sedimentation tank. This is how we can work out. Okay. So surface area for rectangular tank, the surface area is taken as right. It is length into width. For circular tanks, surface area is taken as pi by 4 d square, where d is the diameter of the sedimentation tank, where L is length of the sedimentation tank. This is length, this is width. This one is diameter of the sedimentation tank. This is how we can work out surface area. Then second important concept is detention time. Detention time dt or t. This you can find out by volume of sedimentation tank by Q. So for rectangular tank, this volume is taken as L into B into H. For circular tank, the volume is taken as pi by 4 d square into H. This is how we can work out. For rectangular tank, volume is L into B into H. Then you can find out, you can fix up the dimensions of the sedimentation tank. If it is rectangular tank, we find L, B, H. That's what is called design of sedimentation tank. For circular tanks, we find out diameter of the sedimentation tank and depth of the sedimentation tank. That's it. Depth means liquid depth only. This is how we design the system. In addition to that, we also discussed about flow velocity or flow through velocity is equal to Q by B into H for rectangular tanks. Normally rectangular tanks are popular. Right? For circular tanks, it is radial flow velocity, which is equal to, it is integral R1 to R2. It is what is that? 2 pi into H. 2 pi into H into dr. So it varies from radius of the settling zone varies from R1 to R2. So in that radius only it settled down. Therefore this you can use. This is for circular tanks. Okay. Then coming to one more important design parameter is wear loading rate. Wear loading rate is equal to discharge by length of wear. Discharge by length of wear is known as wear loading rate. Right? Wear is provided on the outer periphery in case of circular tanks, complete outer periphery. In case of rectangular tank, the width of the tank is nothing but length of the wear. So any length is given, we use that. Otherwise, wear loading rate is in general Q by length of wear. Okay. In addition to that, few more things we discussed. How to find out efficiency of the sedimentation tank. Efficiency of particle. Ith particle removed from sedimentation tank is equal to settling velocity of ith particle into V0 into 100. Right? Then you can also work out overall removal of sedimentation tank. That is efficiency of sedimentation tank is equal to, it is sigma percentage of ith particle and their respective efficiencies by 100. This is how we can find out. You can also work out efficiency removal of ith particle by knowing the concentration of ith particle in water. C in minus C out of ith particle by C in of ith particle. If you take and if you multiply by 100, you will get efficiency. This you can also equate to normal equation Vs of ith particle by V0 for which sedimentation tank is designed into 100. Okay. Similarly, overall efficiency or efficiency of sedimentation tank is equal to sigma C in minus C out of all particles by sigma C in of all particles into 100, which can also be equated to sigma Pi into efficiency of ith particle by 100. This way we can work out the things related to sedimentation tank. All these things you have to remember. So this is important, this is important, this is important, this is important. Based on this, is keep on asking questions. This is important, this is important. So this is important, this is important, this is important. So whenever volume is given, whenever we require volume, what we do? Volume is equal to Q into detention time. This is how vice versa we can work out. So this is also important. This is how we can work out the sedimentation tank system. So basis is, so here two things. One is particle property, also important. Particle property is settling velocity. Based on particle property, we adjust sedimentation tank. So sedimentation tank is designed for capturing the particle. Therefore, they are supposed to be comfortable. So for 100% removal of any particle, for 100% removal of any particle from sedimentation system, it has to satisfy two conditions. One is settling velocity of that particle should be greater than or equal to V0. Settling velocity of particle should be greater than or equal to V0. Then 100% removal is possible. That's first condition. Minimum is equal. If it is greater, well and good. And second condition is, right, settling time of particle should be less than or equal to detention time of water. So this L by VH is called detention time. If these two conditions are satisfied, 100% removal is possible. So these are very, very useful relations which we use extensively while solving the problems. All these conditions. This is called settling time of particle. This is settling time. This is detention time. Settling time of the particle should be less than detention time. Detention time something related to sedimentation time. Settling time is something related to particle. Or settling velocity is something related to particle. V0 is something related to sedimentation time. So sedimentation time property and particle property, best compatibility occur between them, the best removal happens. So particles whose settling velocity is less than V0, settling velocity is less than V0, they are partially removed. 100% removal is not possible, they are partially removed. So we can equate settling velocity to V0 for 100% removal condition. Otherwise, Vs is different parameter, V0 is different parameter. There is no link between them. We can link these two parameters only for one condition, that is 100% removal. If these concepts are your thorough, any problem from any book you can comfortably work out. Okay? What I mean to say is, when the particles are settling in water, right, we aim to capture a particle of certain diameter. In the sedimentation tank, we aim to capture a particle of some diameter. Suppose this is a sedimentation tank which we designed for a particular particle to capture 100%. It doesn't mean that this sedimentation tank capture only that particle. It also capture many particles. Particles of all sizes it can capture. But some particles it can capture 100%. Some particles it can, let us assume it is a rectangular sedimentation tank. There is a longitudinal section, length and height. Okay? This sedimentation tank is designed for a particle of diameter d. So this particle it has to capture. So for this particle what we do, we work out settling velocity of this particle. We adjust that V0 slightly more than settling velocity. We see that so V0 is less than Vs. That means Vs is more than V0. First we work out Vs and we see that Vs is more than V0 and we design this, or at least equal to V0. We design this. We design the sedimentation tank. So this particle which happened to enter the sedimentation tank at the height h, it experiences two velocities. One is settling velocity of the particle, try to pull particle downward, and flow velocity of particle, take particle horizontally along with water. This is a particle. This is a particle of diameter d. So which happened to settle down in the sedimentation tank with settling velocity Vh, but this particle also influenced by flow of water. The flow of water try to take particle in a horizontal direction. The settling velocity of the particle caused by the self-weight try to pull particle downward. Particle neither travel horizontally along with water, nor travel vertically along the height of the sedimentation tank. Instead, the particle attain resultant velocity. It travel in the direction of resultant velocity. Particle travel in the direction of resultant velocity. That resultant velocity is this. Resultant velocity is nothing but vector sum of these two. So this resultant velocity direction is this one. So this will take this particle to the bottom of the sedimentation tank. Finally, this particle reach bottom. If this particle is captured to the bottom of this is called trajectory of the particle motion. This is a trajectory, particle trajectory. So when this particle is captured, particles of size larger than this particle, diameter is larger than, so d1 larger than d, they are automatically captured because their settling velocity is much more than, they experience same settling velocity, same flow velocity. Therefore trajectory shift towards this one. Trajectory will be slightly close to Vs. Particle whose diameter is less than, some particle whose diameter is less than d, so that particle has got very low settling velocity. So VH would be same for all particles. Therefore trajectory doesn't hit the bottom of the sedimentation tank. If you see the trajectory of the particle motion for this particle, this will hit the bottom. The particles whose trajectory hit the bottom of the sedimentation tank, they'll be captured. Particles whose trajectory hit side of the sedimentation tank, they escape. So this trajectory hit side of the sedimentation tank somewhere here, so they escape. If particle trajectory hit bottom of the sedimentation tank, they'll be captured. So what we require, capture is required. Any particle whose trajectory hits the side of the sedimentation tank, they escape. Particles whose trajectory hit bottom of the sedimentation tank, they'll be captured. So therefore, not all particles captured 100%. Some particles captured, settling velocity of particles is greater than V0, they'll be captured. Their efficiency is more than 100%, but more than 100% practically not possible. So it is rounded to 100%. Settling velocity of particle is equal to V0. Their efficiency is 100%. They are captured 100%. Settling velocity is less than V0. Their efficiency of particle capture is less than 100%. That is the meaning of partial removal. This is the meaning of partial removal. That's why overall removal is not 100%. So no sedimentation tank capture all particles 100%. Some of them are captured partially, some of them are completely. No sedimentation tank, right, capture or remove all of the particles present in water 100%. So 70-80% removal happens in a sedimentation tank designed with the best practices, best design principles. 70-80% removal is the best capture. So while capturing the particles, depth does not influence particle removal. It is only surface area. Depth does not depend on particle removal. So particle removal depends only on surface area. Surface area, by finding the surface area, we can increase and decrease the particle removal. Particle removal depends on surface area. Surface area of sedimentation tank. So surface dimensions are important. That's why V0 is very important parameter. So depth does not play any role in particle removal. So nowadays we have got tube settlers. The advancement in sedimentation is we are no more using, because busy and congested cities place is the constraint. In busy cities, because of having no space, I can't go with a very large sedimentation tank to capture all of the particles 100%. To capture all of the particles 100%, we require infinite length of sedimentation tank. Large length of sedimentation tank with large surface dimensions are required. Practically that is not possible. Even if you provide also, because of the turbulence, because of the wind currents. So again, turbulence induced in water. When once turbulence induced in water, particles try to escape. Isn't it? So therefore, 100% removal of any particle is not possible. So 70-80% removal itself is a best practice, best capture. So if first condition it satisfies, second condition automatically it satisfies. Suppose for example you see H by VH should be less than or equal to L by VH. So if it satisfies this condition, automatically settling velocity should be greater than V0. Satisfy this. So now for example you see minimum condition, if I take H by Vs is equal to L by VH, so I can write this as Vs is equal to VH into H by L. VH into H by L. What is VH? VH is equal to Q by B into H into H by L. So HH get cancelled. So depth automatically cancel. So what influences particle removal? Q into L into B. What is Q into L into B? Q by surface area. What is Q by surface area? Nothing but Vs. This is nothing but Vs. So therefore, if it satisfies one condition, automatically it satisfies other condition. Q by L into B, which is nothing but Q by surface area, which is nothing but V0. So it satisfies this condition means automatically it satisfies other condition as well. If H by Vs is equal to L by VH, Vs is equal to V0. automatically satisfied. Depth does not play any role in particle removal because efficiency of particle removal is straight away proportional to surface area. If you increase surface area, efficiency also increases. If you decrease surface area, efficiency also decreases. Surface area decreases, efficiency also falls. So by fine tuning surface area, we adjust. Surface area is important parameter. Understood? Surface area influences particle removal. It is not the depth. That point you have to remember. Surface area increases, efficiency also increases. Surface area decreases, efficiency also decreases. If this idea is there with you, any problem from any book comfortably you can work out. There is a cakewalk to you. Last class we solved one problem. Now let us try few PYQs related to sedimentation tank. I try to teach you the best of the problems that were asked in GATE exam, previous GATE exam. Okay. So try to learn through problems. Okay. Let us see first example. Last class we discussed one question. Let us now go with the next question. A rectangular. Mostly they will ask rectangular tanks only for in the exam. You need not worry about circular tanks. Sedimentation tank is treating (1.8) mld of raw water with a detention period of 4 hours. The question number 1. Then find 1 volume of aeration tank. Volume of sedimentation tank. Sedimentation tank required. This is question number 1. Options are given, but I am not giving options to you. You work out. If the allowable overflow rate is, overflow rate is 500 liters per hour per meter square and L is to B ratio is 4:1, then the length required for the tank is So two things have been asked to find out. One is length of the tank, second one is volume of the tank. So with the given information, what information is given? Q is given, detention time is given. Nothing is there except this, nothing is there. Of course, overflow rate is given to work out this, and L is to B ratio is given. Okay, second question. First question is easy only. So we have been asked to find out volume of sedimentation tank. So volume of sedimentation tank required is equal to how to find out? Q into detention time. If you multiply Q with the detention time, we will get volume of sedimentation time. Understood? So Q into detention time is equal to volume. Q is given as 1.8 mld. So for our comfort and convenient, we are converting this into meter cube per hour. So 1.8 mld, if you multiply with 10 power 6, this becomes liters per day. To convert this into meter cube by 1000, now meter cube per day. To convert this into hours by 24. Now it is meter cube per hour. Into detention time is given as 4 hours. So this is in which unit system? Meter cube per hour into hours. So hours get cancelled. Then you are left with meter cube. Come on, simplify. Get the answer. Oh, sound problem. Is it reverberating? Okay, I'll adjust. Raise sound is coming. Okay, I'll adjust 1 minute and see that you don't get any such problem.
Now
How is it? Now tell me, how is the sound now? Comment there. How is the sound now? Come on, NSP Kiran. Kiran, tell me now, how is the sound? Is it okay? How is the sound now? Come on, NSP Kiran. Kiran, tell me now, how is the sound? Is it okay? Still, I need to correct it. Hello, check. Hello.
Hello. Hello. I don't know how to controls.
You can adjust here. Sound system, audio input capture. Okay, it is.
I
don't know how to control. Okay, let us adjust today. So if we simplify how much you get, this is. Okay, let us adjust today. So I'm getting 300 meter cube answer. So let me check once again the device. Let us see the next part. So what is given there? Allowable workflow rate is 500 liters per hour per meter square. Now it's better, I think. So V0 is given. So this V0 is equal to 500 liters per hour per meter square. L is to B is equal to 4:1. That means length is equal to 4 times B, or B is equal to L by 4. Okay. So what you can work out with V0, surface area. Q by V0 is equal to surface area. Q is given 1.8 million liters. Convert into liters per hour. How to convert liters per hour? 1.8 if you multiply with 10 power 6, this is liters per day. Liters per day, how to convert into liters per hour? By dividing by 24. So liters per hour by V0. 500. Okay. So if you work out 1.8 into 10 x power 6 by 24, divided by 500. So it is 150 meters square. Liters per hour by liters per hour per meter square. Which unit system will get? Meter square. Because liters per hour get cancelled, meter square will get. So surface area is equal to rectangular tank, it is L into B is equal to 150 meters square. B is equal to, so from this I can write, so L into L by 4 is equal to 150 square meter. Therefore L is equal to 150 into 4 under root. Come on, how much it is? So 150 into 4 under root. So 150 into 4. So it is 24.49. So it is rounded to 24.5 meters. So options are given, but I have not given options to you. Straight away can work out. This option is there. So second question answer is 24.5. First question answer is 300. So this is how we need to work out. Okay? Next let us see. Next question. Let us solve one good question. In a continuous flow settling tank 3 meters deep, and 60 meters long, what flow velocity would you recommend for effective removal of he has given specific gravity of particle. Kinematic viscosity is 0.01 centimeter square per second. So what have been asked to find out? Flow velocity. Flow velocity means VH. Rectangular tank, no? Because he has given length and depth. So length of the tank is 60 meters. Depth of the tank is 3 meters. Diameter of the particle to be removed is 0.025 mm. Effective removal means 100% removal. For 100% removal of particle size 0.025 mm, what flow velocity would you recommend? Effective removal means 100% removal. So what else is given? Specific gravity of particle is given as 2.65 and kinematic viscosity of water is given as 0.01 centimeter square per second. If you convert this into meter square, 1 by 100 square meter square per second is 1 into 10 power minus 6 meter square per second. So diameter of the particle 0.025 mm. This you can convert into meters. So for 100% removal, what are the conditions? Two conditions are there. Any particle, it has to satisfy two conditions. One is settling velocity of that particle should be greater than or equal to V0. Second condition is settling time of particle should be less than or equal to detention time of particle. Which condition you can use here? Comfortably you can use second condition here. Any condition you can use. If it satisfies first condition, second condition automatically satisfies. Second condition satisfies, automatically satisfies first condition. So any condition you can use as per our comfort. Because we have to work out VH. Since VH is there in this equation, therefore I use this equation. So for that what we require? First of all you need to work out Vs. So for Vs of this particle is equal to, how to find out? Kinematic viscosity is given. So 9.81 into specific gravity is given as 2.65 minus 1 into 0.025 mm converted into meters square by 18 nu. So straight will get answer in meters per second. So if you know Vs, then automatically you will get Vh using that 100% removal condition. So I am working out now calculation part. 0.025 into into 1.65 into 9.81 by 18 into so I got this is 5.62 into 10 power minus 4 meters per second. So what we have been asked to find out settling velocity of the particle, flow velocity of the particle. So flow velocity of the particle is equal to, for 100% removal I am using second condition. Minimum condition I take. H by Vs should be equal to L by Vh. Therefore Vh is equal to Vs into L by H. So Vs I got as 5.62 into 10 power minus 4 meters per second into length is 60 meters given in the question. Length is given as 60 meters, depth is 3 meters. So now work out what is this value? So I got 0.0112 meters per second. That is how we can work out. Whichever unit system they are expected to calculate, in that unit system we can find out later. Sometimes in centimeter per second we express, then we can write in centimeter per second also. Understood now? Hope it is clear to you. So when asked to find out what is the flow velocity would you recommend for 100% removal of particles. So for 100% removal of that particle, you have to maintain a flow velocity of, because flow velocity influences particle removal. Not only VH, this is VH, this is VS. So both of them balances perfectly, right? No. It satisfies that condition, 100% removal happens. So what is this VH? If VS is equal to 0.0, 5.60 into 10 power minus 4. So that 100% we can capture. You can drag this particle to the bottom of the sedimentation tank. Right? That's what you are expected to capture. This is 0.025 mm size particle. So size of this particle is 0.025 mm size particle diameter. Right? What is the flow velocity to be maintained? This particle has got settling velocity Vs. We got this as 5.60 into 10 power minus 4 meters per second. Then what is that VH? So that this particle can brought to the bottom of the sedimentation tank. So you can bring this particle to bottom of the sedimentation tank. We have to maintain this trajectory. To maintain this trajectory, what is the flow velocity to be maintained? That's what we need to work out. Understood now? This particle has to come to the bottom of the sedimentation tank to settle down. Brought back that particle to the bottom of the sedimentation tank. What flow velocity? Because it is influenced by both settling velocity and flow velocity. Settling velocity of the particle and flow velocity of water. Both of them influences particle removal. Understood? We have got the sedimentation topic 4 times in this course. 2 times in water supply and 2 times in wastewater. So therefore it is very important topic. 100% you will get 1 question from sedimentation topic by default in GATE exam. Sedimentation topic is very important. Okay. Now let us try one more question. Simple questions easily can work out. Let us see some good questions. Example. Tia, this is 2 now? Okay. A rectangular sedimentation tank is designed. For a surface overflow rate of 12,000 liters per hour per meter square. What percent of suspended particles of diameter would be removed? This is also asked in GATE exam. Dash as given. This is GATE 99 question. GATE 1999 question this is. What is the percentage removal? What percent of suspended particles of diameter would be removed? What percentage the particles of diameter 0.03 mm are removed? Percentage removal of any particle. Nothing but efficiency of particle removal. Ith particle removed. So it is efficiency of ith particle. The settling velocity of ith particle by V0 for which sedimentation tank is designed into 100. So in this case what is given? V0 is given 12,000 liters per hour per meter square. in settling velocity what to find out. To find out settling velocity, what is given to you? Diameter of the particle is given. In addition to that, what else is given is kinematic viscosity also given. So as given in brackets, kinematic viscosity is equal to 0.0897 mm square per second. Then specific gravity of particle is given as 2.65. This information also given to you. So using this information comfortably you can work out settling velocity of particle. So what is given? V0 is given as 12,000 liters per. See, the unit system is strange. You convert, because settling velocity we calculate in meters per second. Let us convert this also in meters per second. So 12,000 means you convert into meter cube, what happens? This is 12 meter cube per hour per meter square. Because 1 meter cube is equal to 1000 liters. 1 liter is equal to 1 by 1000 meter cube. So divided by 1000, 12. So this is nothing but 12 meters per hour. I am converting this into hours into seconds. 1 hour is equal to 60 by 60 seconds. 12 by 60 into 60. Come on, work out. So it is 12 by 60 into 60. So it is 3.33 into 10 power minus 3 meters per second. Okay? V not we got. So Vs we have to work out. So Vs is equal to, it is G into S minus 1 d square by 18 nu. But d is given in mm, 0.03 mm. So 0.03 into 10 power minus 3 meters. Kinematic viscosity is given as mm square per second. 0.897 mm square per second. This you convert into meter square per second. 0.897 into 1 by 1000 square meter square per second. So that means how much you get? 0.897 into 10 power minus 6. This is nothing but 0.897 into 10 power minus 6 meter square per second. Now let us work out this settling velocity of particle. Settling velocity of particle is equal to G into S minus 1 d square by 18 nu. So G is 9.81, specific gravity is 2.65 minus 1, 0.03 into 10 power minus 3 whole square by 18 into 0.897 into 10 power minus 6 meters per second we get. Can work out this value, all of you. .81 into correct now? I got this as 9.02 into 10 power minus 4 meters per second. Therefore, percentage removal of particle is equal to efficiency only. What do you calculate efficiency? Come on, tell me. So it is settling velocity of the particle by V0 into 100. Settling velocity we got 9.02 into 10 power minus 4. This is 3.33 into 10 power minus 3 into 100. By 3.33 into 10 minus 3. So I got 27.09 percentage. So we express this in percentage. So that was the answer for this question. 27.09. Are you following me? Doubts are there, you can message to me. There in the comment box you can message me. I'll clarify your doubts. Okay? You can message me. Any doubt is there? Straight away you can message me. Let us go ahead with the next question. Example number 4. Sedimentation topic is very important. So more numericals is all, more you become familiar with concepts. So once you become more familiar, more comfortable, you can work out the problems in exam. 100% you will get one question in the exam. Okay? That much I can assure you. Now let us solve one more good question. So design a rectangular sedimentation tank. Okay. Different kind of questions let us work out. A plane, these are all old GATE questions only. Has dimensions 100 meters by 50 meters by 3 meters and receives flow 1 lakh cubic meter per day. Calculate the surface overflow rate in meter cube per meter square per day. Okay, that's a question. And the diameter of the smallest particle which would be removed 100%. One more question is there. And the diameter of the smallest particle which will be removed 100%. Take density of particle .65 gram per cc and kinematic viscosity of water is 1.02 into 10 power minus 2 centimeters square per second. This is what is given in the question. Okay? So two things have been asked to find out. One is surface overflow rate in this unit system. Second one is the diameter of the particle is 100% removed. And he has given this information. So two things are there. If you know diameter, you can find out percentage removal. If you know percentage removal, you can also work out diameter. That is vice versa. It is not a big deal. So what is given to you? Dimensions of the tank is given, Q is given. So you have to read this as L into B into H. L into B into H of the tank is given as 100 meters by 50 meters by 3 meters. You have to read like that. It is always 100 meters, larger dimension. Width is 50 meters and depth is 3 meters. Okay? That's the meaning of this one. And Q value is given as 1 lakh cubic meter per day. And you have been asked to find out what first surface overflow rate in meter cube per meter square per day. So surface overflow rate V naught is equal to Q by surface area. Rectangular tank surface area is L into B. So substitute Q in meter cube per day, and this is in meter square. Automatically you will get answer in meter cube per day per meter square. So it is 1 lakh by 100 into 50. So it is meter cube per meter square per day. You can write like this, or you can also write like this, meter cube per day per meter square. Both are same only. Okay? So how much it is? It's coming around 20. Because this 0 cancel, these 2 zeros cancel. So 5 2s are highest kind of question. Meter cube per meter square per day. That was the answer for first question. So simple and so easy. Clear now? First question answer is clear or not? Let us see now. Second part of this question is, what is the diameter of the particle that will be removed 100%? So for 100% removal, what is the condition? Two conditions are there. Condition 1 is settling velocity should be greater than or equal to V naught. Condition 2 is H by Vs should be less than or equal to L by Vh. I can use first condition because if I know settling velocity, I can find out diameter. So I'll take Vs greater than or equal to V naught. Minimum condition I'll take Vs is equal to V naught. Greater than or equal. So minimum condition is Vs is equal to V naught, worst case. So which is nothing but 20 meter cube per meter square per day. Already we got this. This is nothing but 20 meters per day. So how to convert meters per day into meters per second? So it is 20 by 24 into 60 into 60. Days into seconds. Okay? So Vs we got. Once you get Vs, we know Vs equation. What is Vs equation? Vs is equal to what is given in this question? Kinematic viscosity only given. Okay? Specific gravity of particle is given, density of particle is given. Okay. So what is given to you? Density of particle is given. Specific gravity you can work out if you know density of particle. Density of particle by density of water. This is given as 2.65 gram per cc. This one. So gram per cc by gram per cc. Density of water is 1 gram per cc is also equal to 1000 kilogram per meter cube, which is also equal to 1 ton per meter cube. All are one and same only. Okay? So, because he has given gram per cc, we took gram per cc only. 2.65 indirectly. Then, kinematic viscosity is given as 1.02 into 10 power minus 2. What unit system is given? Centimeter square per second. How to convert centimeter square into meter square? By 1 centimeter square is equal to 1 by 100 square meter square per second. So if you convert this into meter square per second, it is 1.02 into 10 power minus 6 meter square per second. Now substitute. So settling velocity is equal to g into s minus 1 d square by 18 nu. So in this everything is not except d. So settling velocity is how much we got? 20 by, here it is there, 20 by 24 into 60 into 60. So from this I can write
settling velocity
is given as 20 by 24 into 60 into 60 is equal to G 9.81, 2.65 minus 1, D is unknown. Of course, it is given in meters only, 1.02 into 10 power minus 6. So from this you will find out D. D is equal to size of particle that will be removed 100%. We will get answer in meters, then later you can convert into mm. Come on, work out. So it is 18 into 1.02 into 10 power minus 6 into 20 by 24 into 60 into 60. Divided by 9.81 into 1.65 under root. D square is equal to this, D is equal to how much? So I got this 1.62 into 10 power minus 5 meters. So 1.62 into 10 power minus 5 meters means how many mm? Into 1000. Multiply 1000, we will get in meters. 0.0162 mm. That is how you can calculate. Or you can write 16.2 mm. 16.2 into 10 power minus 3 mm. This way also can represent. That is the size of the particle. Understood? That was the answer for that question. Hope we are solving different kinds of questions. Okay, for exam point of view. Let us try one more question. Example. Example 5. An ideal horizontal flow settling basin three meters deep, having surface area 900 meters square. Water flows. This question has been asked in GATE 2003 at the rate of 8,000 meter cube per day at a temperature, at water temperature 20 degrees Celsius. In brackets he has given dynamic viscosity at 20 degrees Celsius. He has given like this. Dynamic viscosity and density. Density of water is given as 1000 kilogram per meter cube. Assume Stokes law to be valid. Of course, for all settling operations, Stokes law only based. Stokes law to be valid. The portion of spherical particle. The proportion of spherical particle. Spherical particle. .01 mm in diameter with the specific gravity 2.65 will be removed. So what you have been asked to find out? Proportion of particles removed. What you have to understand is proportion of particles removed means nothing but a percentage of particles removed or efficiency of particle removal is asking. So to work out efficiency of particle removal you require two things. Of course options are given. This question has been asked in GATE 2003. Options are given 32.5, 67, 87.5, D 95.5 like that. But tick mark one. Let us not go with options. Let us work out the problem. Come on. Try. All of you try.
Okay.
So the proportion of particles removed is equal to
Nothing but
percentage of particles removed. Nothing but efficiency. This is what answer. We know that efficiency is equal to settling velocity of particle by V naught into 100. So there is some information related to settling velocity. V naught is not there. You can find out settling velocity. V naught. V naught is not there. Vs also not there. V naught also not there. But information is there to work them out. So once you know Vs and V naught, a simple ratio that will give percentage removal of these particles from water. Understood? So to find out settling velocity, size of the particle is given. Okay. Dynamic viscosity is given. Therefore, I am using this equation. So because he has given size of the particle is 0.01 mm. So it is 0.01 into 10 power minus 3 meters. Dynamic viscosity is given. No need to convert because 1 kilogram per meter second is 1 Newton meter per second also. So rho P is not given, indirectly given. So specific gravity of particle is rho P by rho W. So from this you can write rho P is equal to specific gravity into rho W. So it is 2.65 into 2.65 only, no? Into 1000. So it is 2650 kilogram per meter cube. Now formula substitution. You can work out settling velocity of particle. Settling velocity of particle is equal to 9.81 into 2650 minus 1000 into D is 0.01 mm converted into meter square, meters to 18 into 10 power minus 3. Come on, work out. Come on, fast find out. So your participation should be more, not my participation. I'm working out using virtual calculator.
So I got this as
8.99 into 10 power minus 5 meters per second. Okay? And V naught is equal to Q by surface area. Q is given surface area is given. So Q is given as 8000 meter cube per day. Surface area is 900 meters square. Meter cube per day by meter square. We will get answer in meters per day. But we need to substitute in meters per second. So 8000 by 900. It is 8.88 meters per day. To convert into meters per second, it is 1.02 into 028 into 10 power minus 4 meters per second. Okay? Then percentage removal is efficiency, settling velocity of particle by V naught into 100. So it is 8.99 into 10 power minus 5 by 1.028 into 10 power minus 4 into 100. Into 8.99 I got 87.45. So you can round it to 87 point. You can take 1.02 otherwise. So 8.99 by 1.02. So 88 point something you will get. I got 87.45. Okay, 1.028. This is 8.99 something. Okay. So options given are 32.5, 67, 87.5, 95.5. So you can tick mark 87.5%. That was the answer for this question. It is rounded to 87.5%. Okay. So for every model, I am trying to solve one question so that you become familiar how to solve questions in the exam. Any kind of question let him ask, we can comfortably work out. Next example. Example 6. This is also a typical question. Good question. GATE 2009. A horizontal flow primary clarifier treats water or anything. Wastewater he has given wastewater, but I am converting into water. In which 10% he has given wastewater. Concept is same only. 10%, 60% and 30% of particles have settling velocities .1 mm per second, 0.2 mm per second and 1 mm per second respectively. What would be the total percentage of particles removed? If it operates, if clarifier operates, clarifier also same as sedimentation tank only. Synonym for sedimentation tank. If clarifier operates at a surface overflow rate of
43.2 meter cube per
meter square day. This is how it is. This was the question. Try, think all of you. So there are three particles of different sizes present in different percentages in water. 10% is one type of particle. Second type of particle present 60%. Third type of particle present 30%. They have got settling velocity is 0.1 mm per second, 0.2 mm per second, and 1 mm per second respect. That's given settling velocities. All these particles are settling in same sedimentation tank, which is designed for a surface workflow rate 43.2 meter cube per meter square per day. So for all particles, V0 is same, but VS is not same. Then what is overall removal? So I already mentioned you. Overall removal of all particles is equal to overall percentage removal of all particles. Is efficiency overall, efficiency O, which is equal to sigma Pi into efficiency of individual particles by 100. Okay, for individual particles you have to find out efficiency. Efficiency of individual particles, how you can work out? Settling velocity of individual particles by V0 into 100. So for that V0 is given as 43.2 meter cube per meter square day, nothing but 43.2 meters per day. Meter square cancel meters per day. So 43.2 by 24 into 60 into 60 meters per second. But settling velocities are given in which unit system? Mm per second. Let us convert into mm. Into 1000 mm per second. So if you convert this into mm per second, how much you get? Let us see. So 43.2 by 24 into 60 into 60. Into 1000. 0.5 mm per second. Okay.
Therefore, to find out overall efficiency,
what I do is, so there are three particles present in water or wastewater, whatever it may be, whatever may be the medium. Concept is clear. So particle 1, 2, 3 particles. Percentage removal, percentage present, that is Pi. Pi is nothing but percentage of ith particle present in water. So it is Pi. This is percentage. That is also given to you. 10% of first particle.
Particle 1 is
10%, particle 2 is 60%, particle 3 is 30%. So total is 100%. If you sum up, you should get 100. So the settling velocities are given in mm per second. Right? So it is 0.1 mm per second, 0.2 mm per second, 1 mm per second. Therefore, efficiency of removal of each particle is settling velocity of this particle by V0 into 100. So V0 is same now. This also we work out in percentage. So particle 1. So settling velocity is 0.1, V0 is 0.5 into 100. So particle 1 are 20% removed. Particle 2, 0.2 by 0.5 into 100. So they are removed 40%. Particle 3, 1 by 0.5 into 100. So we are getting 200%. Practically 100% only possible. So whenever you get more than 100, since efficiency is greater than 100, so it is equated to 100% only. So it is 100% removed, third particle. Therefore efficiency overall is equal to sigma pi into efficiency of ith particle by 100. So 10% of particles, 20% removed, 30% of particles, 40% removed, 60% of particles, 100% removed. Therefore overall efficiency is equal to this much. So if we take 200% there, we will go wrong. So for that wrong also, if you think wrong also, there is one option matching. So you should be careful. Come on, work out now. Ten into 20 plus 30 into 40 plus 60 into 100. That's all, no?
Overall removal. I'm not getting properly. What happened? Oh,
10, 60, 30. So I took in wrong way. That's why I'm getting wrong. This is 60%. Sorry. Last one is 30%. So see now silly mistakes you commit, will go wrong. This is 60. Answer not getting answer. This is 30. Now we'll get 10, 60, 30. Order you have to follow. So 10 into 20 plus 60 into 40 plus 100 into 30. 30% of the particles, 100% by 100. So it is 56%. If we take 200%, we will get 86. That is wrong. That was the answer. So, let him ask any question. Your concept is right. Obviously, you never ever go wrong. You always go right only. Okay? Let us try one more question. Example 7. All these problems you practice, from this only we will get one question in the exam. The suspension of sand-like particles in water
with particles
of diameter
0.1 mm and below
is falling into a sedimentation tank.
Okay. At a
0.01 meter cube per second. He has given like this. G is given as 9.8 meter per second square. Specific gravity of particles is given as 2.65 and kinematic viscosity of water is 1.0105 into 10 power minus 2 centimeter square per second. Right? He has given like this. Yes means second only. The minimum surface area. The minimum surface area in meter square required for this settling tank to remove particles of size 0.06 mm and above with a 100% efficiency is dash. This question has been asked in GATE exam, GATE 2014. Good question. To confuse you, he has given diameter of the particles 2 times. Here is given and here also given. So he mentioned that water contain particles of size. Water contain particles of size D less than or equal to 0.0 point. What is it? 0.1 mm. This is given. So water contain all particles of size less than 0.1 mm. In this what particle you are expected to find out what is surface area of sedimentation tank to capture particles of diameter greater than or equal to 0.06 mm with 100% efficiency. That is what the question. So which particle you have to able to capture 0.06 mm. So 2 times D is given, but which D you have to choose? This D you have to choose. What is surface area required to capture particles of size greater than or equal to 0.06. 0.06 mm diameter is captured, larger particles automatically captured. Understood? Smaller particles captured means larger particles are easy to capture. Small particles only difficult to capture. If small particles is captured, large particles automatically you can capture. Tough exam you clear, easy exams automatically you can clear. What are the easy particles? Large particles are easy to capture because their self-weight is more, therefore easily they settle down. Small particles self-weight is less, they are difficult to settle down. Therefore, if you could able to capture small particle, large particles automatically they sedimentation tank capture from water. Okay, that was the concept. Okay, further what is given? Q is given 0.1 meter cube per second. So what is required? V naught you have to find out. Q by V naught is equal to surface area. So V naught is not there. V naught to find out, Vs you can take. 100% removal condition is there. From there you can calculate Vs. So for 100% removal condition is Vs should be greater than or equal to V naught. So I will calculate Vs. Vs is equal to G into S minus 1 d square by 18 nu. So as given G value 9.8, specific gravity is 2.61. So 0.06 mm, 0.06 into 10 power minus 3 meters whole square by 18. Kinematic viscosity of water is given 1.05. 1.0105 into 10 power minus 6. This is also substituted in meter square per second. Actually given in centimeter square per second, 0105 converted into meter square per second. So that you get an answer in meters per second. Come on, work out. Understood now? Otherwise I'll write. Next page I'll write. So with full clarity, with crystal clear clarity, you have to understand the concept and you have to work out the problems. Because GATE always try to confuse you. So with the practice, you can overcome all such hurdles in understanding the concept, and comfortably you can work out the problem in the exam. Practice makes things perfect. Okay. So kinematic viscosity is given 1.0105 into 10 power minus 2 centimeter square per second. So I am converting this into meter square per second. So we convert. This become. Now we can work out. G value given 9.8 only in the question. Let us use that value given in the question. 0.06. Which part of diameter? Here 2.1 also there, but it should not be taken. Because you mentioned that water contains the particles of size less than or equal to 0.1 mm. But you are able to capture 0.06. 0.06 is captured automatically larger than 0.06. You can capture. Therefore, 0.06 into 10 power minus 3 only we take into account here. 18 into nu. Can work out. So I got this as 3.2 into 10 power minus 3 meters per second. Therefore, for 100% removal, condition is Vs should be greater than or equal to V naught. Therefore, I will take V naught is equal to Vs, minimum condition. 3.2 into 10 power minus 3 meters per second. Therefore, surface area of sedimentation tank is equal to, that's what you have been expected to calculate. sedimentation tank required. We are expected to calculate that value. Okay? Q by V naught. Q is given as 0.1 meter cube per second. V naught is V naught value 3.2 into 10 power minus 3. So meter cube per second by meters per second. Straight will get surface area in meters square. Point 0.01 meter cube per second. Okay. This is 0.01. So 0.01 by 3.2 into 10 power minus 3. So it is 3.125 meters square. That was the answer for this question. So you are supposed to have a sedimentation tank of surface area 3.125 to capture this particle 100% from water. Understood? Let us try one more different question. Example 8.
Okay. This is also a very good question. Consider a primary sedimentation
tank in water treatment. The surface overflow rate of 40 meter cube per meter square per day. The diameter of the spherical particle will have, is not given day, D is given. D means day, S means second, H means hours. The diameter of the spherical particle which will have 90% theoretical efficiency.
Theoretical removal efficiency.
In this tank is dash microns. He has given question like this. We will ask you to find out what is the diameter of the particle in microns, which is removed only 90%. To support this question, some data also given to you. Assume that settling velocity particle not described by Stokes law. Density of water. Take density of water is equal to 1000 kilogram per meter cube. Density of particle is equal to 2650 kilogram per meter cube. G is given as 9.81 meter per second square. Kinematic viscosity is given as 1.10 into 10 power minus 6 meter square per second. This information is given, support information. So far we calculated the things related to 100% removal. What is the size of the particle that is only removed 90%? That you have to work out. Come on, try. That we have to find out in microns. So what is the equation? Efficiency is equal to settling velocity of particle by V naught into 100. So efficiency is given as 90% and V naught is given as 40 meter cube per meter square per day. Right now? So therefore, from this can't work out settling velocity. Therefore, settling velocity is equal to efficiency into V naught by 100. So 90% into 40 by 100. It is 36 meter cube per meter square per day, which is nothing but 36 meters per day, which is equal to 36 by 24 into 60 into 60 meters per second. So we know that this VS you have to take. If it is 100% revolve, definitely we will take VS as 40. But it is not 100% revolve, only 90%. For 90% revolve, what is size of the particle that will be removed? So VS for that particle is this much only. Therefore we know that VS is equal to, so once you know VS, you have to calculate diameter of the particle. Comfortably you can work out. G into S minus 1 d square by 18 u. Kinematic viscosity square, I am using this formula. So I got my VS 36 by 24 into 60 into 60. G is given 9.81 meter per second square in the question. But specific gravity is not given. Specific gravity of particle is equal to density of particle by density of water. So it is given 2650 by 1000, indirectly given it is 2.65. 9.81 into 2.65 minus 1, D is unknown, by 18 into kinematic viscosity is given, proper unit system only, 1.10 into 10 power minus 6. So from this diameter of the particle that will be removed 100%, first we will get in meters, then you can convert into microns. Come on, work out. Calculation part. Help me in calculation part. Come on. So I got this is 2.257 into 10 power minus 5 meters, but I have been asked to express in microns. 2.257 into 10 power minus 5 into 10 power 6 microns. 1 meter is equal to 10 power 6 microns. So multiply this with 10 power 6. So I got 22.57 microns. So 22.57 microns, they are 90% removed. 100% removal means 40 will take there. Instead of 36, will take 40. Understood? Good question. Try one more question before we conclude. Example 9. So we solved decent number of questions. So we have thorough practice in a. This is also GATE question, wastewater treatment plant. This has been asked in GATE 2015. Last question also GATE 2015. This is also GATE 2015. This is also GATE 2015. See now 2 questions asked from same topic. Because this topic is there 4 times in this course. In a wastewater treatment plant, primary sedimentation tank design, at water flow rate of 32.5 meter cube per day per meter square is 32.5 meters long, 8 meters wide, and liquid depth 2.25 meters. The length of the weir is 75 meters. The weir loading rate meter cube per day per meter is dash. This is also GATE 2015 question. So now 2 questions came from same topic. So simple, so easy it is. What is weir loading rate equation? Discharge by length of weir. Length of weir is given. That is 75 meters. Length of weir is given to you as 75 meters. But what else is required? Q is not given, but indirectly given. Overflow rate is given, this is given. From this we can find out Q. Normally Q is a known component, but in this question Q is unknown. Strangely. Okay, no problem. So how to find out Q? Using overflow rate. Surface overflow rate is equal to Q by surface area. What is Q by surface area? L into B. Therefore from this you can write Q is equal to, it is V naught into L into B. So V naught is given as 32.5. Length also 32.5. Width is 8 meters. This is meter cube per day per meter square. Meter cube per day per meter square into meter this is. So this meter square cancel out. Then you are left with meter cube per day. Okay. So weir loading rate is equal to Q by length of weir. So Q is 32.5 into 8. Length of weir is given in the question, 75 meters. So it is meter cube per day by meter. Therefore we will get answer in meter cube per day per meter. So just by adjusting the unit system also you will get answer. It is 112.66 meter cube per day per meter. That was the answer for this question. So this is how we can work out problems in plain sedimentation tank. I am searching for one more problem type of question. This question is been asked in GATE exam.
I don't have that question.
That question is missing with me. Concentrations are given. We are expected to find out percentage removal, overall removal.
Let me
Take that question. With that question we'll wind up. Okay, that is also a very good question. Question bank is there with me. Okay. This question is been asked in GATE 2000, I think 17 or 18. I don't know. So next, one more example. An ideal settling basin is designed with a surface overflow rate 1 meter cube per meter square per hour. Particles have their discrete settling velocities and concentrations are as follows. So one is particle type, settling velocity, initial concentration. This is given in the question in milligram per liter. This is settling velocity is given in meters per hour. So particle type 1, particle type 2, particle type 3, particle type 4. He has given these values 1, 0.5, 0.1, 0.05. Initial concentration for all particles is same, 100. In addition to that, which one of the following gives correct estimate of overall removal of particles? Overall. Find overall concentration of particles removed. Overall removal of particles. This option is given to you 4 options. He has given like this. Which one of the following? Continuation. Okay, I'll write next page. Which one of the following gives correct estimate of overall removal of particles per hour? So option A is 65 milligram per liter, option B is 165 milligram per liter, option C is 265 milligram per liter, option D is 365 milligram per liter. So what is given to you is, take table, particle, right, their settling velocity in meters per hour given, then where C naught is given. Initial concentration is C naught. So what I would find out? Efficiency. Efficiency is equal to settling velocity by V naught. Then concentration of particles removed is equal to, what is that concentration of particles removed? C in minus C out, which is equal to efficiency into C in. This is C in. Okay, I'll take C in. Okay. Let us see. 1, 2, 3, 4. He has given settling velocity is 1, 0.5, 0.1, 0.05. C in is 100 for all. So V naught also given 1. So V naught is given as 1 meter per 1 meter cube per meter square per hour. Nothing but 1 meter per hour. So it is 1 by 1 into 100. So efficiency 1 is equal to particle 1 is 100% removed. This is also percentage. Efficiency of particle 2 removed is 0.5 by 1 into 100. So they are 50% only removed. Efficiency of particle 3 is 0.1 by 1 into 100. They are 10% removed. Efficiency of 4 is 0.05 by 1 into 100. Only 5% removed. So concentration of particles removed is 100%. 100 milligram per liter is removed. So therefore 100 milligram per liter this is. 100% of 100 milligram per liter. This is 50% of 100 milligram per liter. Okay? This is 50 milligram per liter is removed. This is 10% of 100 milligram per liter. 10 milligram per liter is removed. This is 5% of 100 milligram per liter. 5 milligram per liter. So therefore overall removal means it is sigma C in minus C out is equal to, it is 100 plus 50 plus 10 plus 5, which is equal to 165 milligram per liter. That was the answer for this question. So what do you have to tick mark? 165. So overall concentration of particles removed is equal to overall concentration of particles. So removed is equal to, it is sigma of C in minus C out. So which is equal to 100 plus 50 plus 10 plus 5, it is 165 milligram per liter. That was the answer for this question. Understood? Okay then, before I close, let me show you something. Okay? Some promotional content is there. Just go through this. So Unacademy is offering you mock test exams. So many modules are available. You can choose whichever suitable to you. So mock exams they are conducting. You can use my code GATE Civil. Thank you. Again we'll meet tomorrow. Tomorrow morning I'll take. Tomorrow morning 10 o'clock. 10 a.m. I will take. 10 a.m. to 12 p.m. I will take class. I'll start coagulation. Sedimentation added with the coagulation. Okay.